Okay, so we looked at one method of dislocation observation, which is surface method, where you do etching and then you observe under optical micrograph. And in fact, it is not all over. Let us see, there are few more information about this. So, when I said that it is useful for dislocation density less than 10 to the power, it should be 10 to the power 10 meter per square. If it is more than that, what will happen? What you would see is just etch pits, lots and lots of etch pits on the surface. So, these what you would see is etch pits. For example, people have done study in tungsten crystal, and only when they are far distant, there is certain amount of distance between them, that you will be able to resolve it, and that is why this method works best when dislocation density is less than 10 to the power 10 per meter square. Now, I earlier mentioned when I started this surface method that this method has also been used for studying dislocation motion, and what people have done is, for example, you take when the dislocation density is obviously when small, you make a etching somewhere and you observe something like this, and then actually it will be much larger, and let us say stress is applied such that the dislocation is expected to move in this direction. So, what will happen is that the after, let us say, the applied some stress for certain amount of time and the dislocation has, so here was your so here was your original dislocation. So, this is let us say T1. Now, let us say some stress was applied for certain amount of time and this dislocation has moved. So, what will happen? This same thing you would observe over here. And then, so this is at T2, and then let us say you apply the stress for some more time, and then you may see this over here. So, by and in fact, what is interesting is that you can even see the remnants of the earlier dislocation, meaning what you would see over here, it would look something like this, because it is getting etched and the dislocation on the bottom has vanished. So, it will get a flat bottom and you would see something like this. So, if you have after the third time interval, when you etch it, you would see a much larger etch pit over here, but with a flat bottom, because the dislocation has moved out, and since this one moved out only a small time ago. So, you would see a smaller etch pit with a smaller bottom surface, and it will be like this, and only in this you would see a sharp, where it will be more like a diamond shaped indent into this, and this clearly tells you that the dislocation is present here, and it was present earlier here, and it was present earlier here, and when it has moved away, you see a flat bottoming of it, and by measuring the distance and know the time, you can find out that for given stress and the given amount of time, how much the dislocation moves. You can find out the velocity and other related information can be obtained. So, this is one method, which is the surface method. Now, let us look at still another method, which is decoration method. Now, remember that in optical microscope, dislocations cannot be observed directly, and therefore, you need a third material to actually reveal it, and this is where decoration method comes into picture. So, for example, this people have done study by doping. So, in potassium chloride, people have doped it with silver chloride during the melt stage itself. Okay. So, once it has solidified, it has some amount of very small fraction of silver chloride present in potassium chloride, and then people anneal it, something like aging operation, anneal it to precipitate out silver precipitates, silver particles. And where will it preferentially precipitate? Obviously on dislocations, near the dislocation core, because that is the large free volume area where the additional particles can easily come and attach to. We will talk more about it in the next part of the course, where we talk about plasticity aspect. So, silver particles preferentially precipitate out silver particles preferentially at dislocations. And then it can be seen by, can be observed by optical micrograph. So, what you would see is, like let us say there is a regular spacing of dislocation. So, the dislocation may be, let us say, like this, but you would not have observed these dislocation lines per se. But now that there are silver precipitates, so what will happen is that there will be silver precipitates all around this, and you are not observing the green lines when you look at the it through the optical microscope, but what you would be looking at these will be these orange particles which represent here the silver particles. So, you would know that this is where the dislocation lines are present. So, this is the decoration method which is also used to find or to observe dislocations. Next, let us move on to the most powerful technique, which is transmission electron microscopy, which is the method which was used for the first time to observe dislocation. So, note that we are not saying any electron microscopy. So, for example, scanning electron microscopy cannot show you dislocations, only transmission electron microscopy can show you, and that is because transmission electron microscopy depends on diffraction. So, near the wherever there is a dislocation, the planes around it get distorted, and so the diffraction takes place, and that diffraction is what leads to. So, for example, let us say there are certain planes like this, and this is your half plane. So, the dislocation line is somewhere over here, and so let us say the dislocation line is over here, and your beam is coming like this. So, the beam is coming in and getting diffracted, and some of the beam which falls like this will get diffracted in a different direction because of what is called as diffraction vector. We are not going into the details of this transmission electron microscopy because that is a course in itself, but understand that there is a diffraction vector, and wherever the planes are distorted, you get a distorted line, and hence what when you look at the image that is formed on the bottom side where there is, so all the lines come here, but some of them get diffracted, and therefore, what will happen wherever there was dislocation, it will appear as dark lines. So, what you would see is something like this. So, let us say this is a thin foil which has been observed, and that thin foil will have lines like this. What do these lines represent? These are dislocation lines. So, this is one of the best methods to observe dislocation lines, and particularly if the density is high. So, this method works even if, so this method is useful whether density is high or low. So, transmission electron microscopy is regularly used, and even to calculate dislocation density people use this method. So, you can take micrographs and over there you can count lines where you are measure the length of the lines to find out the density of the dislocations. So, this is one method that is regularly used. Another method which is known to be used for direct observation is X-ray diffraction tomography. So, this is a tomography, meaning you are taking X-ray diffraction in cross sections. So, usually a crystal is rotating and X-ray diffractions are done along the direction, one particular direction, and it keeps rotating. So, it takes a cross section for all the overall material, overall system, and then all these images are integrated. Now, over here wherever there is a dislocation, something similar to TM, wherever there is a dislocation, what will happen? Wherever there is dislocation, what will happen? What will happen is something similar like I said in TM, and over there the intensity would vary. So, intensity would vary, and this can be directly photographed. And in fact, people have done this for something like silicon crystal. So, in silicon crystal people when they have done X-ray tomography, people have seen images like this, and you can see this even in Hull and Bacon. So, all these lines represent dislocation lines. So, X-ray tomography, because of the difference in intensities where dislocation line is present, what you observe is a photographic image like this which directly represents the dislocations. However, the caveat here is that this is also only good for low density of dislocations. Why? Because usually the resolution of this tomography method is very poor, is very low compared to TM. You cannot compare it with TM anyways, it is orders of magnitude different. So, this method is good only for low density dislocations. So, now you can see that there are so many different methods to observe dislocation, and you would also realize that TM is the most powerful method. It does not matter what is the dislocation density, and you can measure the dislocation density using this particular technique. So, now we have covered a lot of aspects about dislocation. So, for example, we have covered stress, strain, what is the stress strain field around a dislocation. We have looked at their elastic energy that is stored. We have looked at different kinds of dislocation, whether it is edge or screw. We have looked at forces or stresses that act on the dislocation which leads to their motion. We have also looked at interaction between dislocation. So, if there is a large pool of dislocation, or like in a material, like if you are looking at a microstructure, there are several dislocations, and each one of them will be influencing, or basically it has a stress field because of which it will cause an influence on the other dislocation. So, we have looked at it, which was given by the relation Peach-Kohler relation. So, this is the most important when it comes to understanding the interaction between dislocations or evolution of dislocations. We have also looked at dislocation motion. It takes place by, we saw that it can take place by glide, which is usually room temperature phenomena, while there is also a process like climb, which is usually dominated at higher temperature. Then we also looked that there is cross slip, which is possible particularly only if, in the case of screw dislocation. And we also looked at the fact, or we found that there is a minimum stress required, critical resolved shear stress, or we can also, we looked at it from atomistically, which is the Pearl-Navarro stress. So, there is a Pearl-Navarro stress which must be overcome for the dislocations to move continuously. And we also looked at intersection, and we also looked at strain rate and velocity of dislocations. So, now having looked at all of this, there is now we are in a position to be at least at the fundamental level without talking about a specific system, because when we talk about a specific system, which will come as the next stage, we can at least say how the dislocations would react in the presence of others or because of the presence of other stresses, and because of that will they move, how much they will move, what will be the final configuration, where will be the zero energy configuration. And this study is called dislocation dynamics. So, all that we have established so far, we are in a position to describe what is dislocation dynamics. All the important elements that are needed for dislocation dynamics are have already been covered. What we need to cover in later stages are to look at dislocations in a particular system in more depth, for example, FCC, BCC, HCP or superlattice structures, which we will come to in the later stage. So, but for now let us understand what is dislocation dynamics. Dislocation dynamics, it is study of evolution of dislocations under internal or external stresses. So, this describes, for example, there are dislocations will be applying stresses onto other or and which will result in forces onto them, or because you are applying stresses externally, because of which there will be forces again on the dislocation, and then it should cause motion of the dislocation. So, we should be able to using, if we know all the values, that is stress, strain, Pearl-Navarro stress, and we know the velocity, strain rate, all these concepts we have, then we should be able to, using the dislocations, the information about dislocation, we should be able to predict phenomena like pile up. What is pile up? We will come to about in more detail, but it is just the dislocation getting accumulated at one place when you apply stress. Now, when you apply stress, what is happening? Everything that is happening is understandable in terms of concepts that we have given over here. So, this is where dislocation dynamics come into picture. Whatever phenomena that is observed should be, we should be able to explain, or in fact even predict or simulate using the concepts here. So, what is the governing equation over here? The governing equation is F equal to ma. There is some force acting onto the dislocation, because of which it should accelerate, meaning it should move. So, these are the two important important terms that we have over here, F and ma. Now, let us look at it in more in a greater detail. What is the force relation that we have? If you remember, the force relation is already with us, which is known as the Peach-Kohler relation. where we had written like this, and now I will put sigma as sigma net, meaning the overall stress that is acting onto a particular dislocation, dot B cross E or U, whatever you want to write. So, force part is already known to us. Now, A can be written as d2 x by dt square. So, we can say F is equal to m d2 x by dt square. But there is also some amount of resistance to the motion of dislocation, and where does this resistance come from? If you remember, there we talked about, when we talked about the velocity, that there are damping forces. So, this damping forces can be related in terms of B, and it is proportional to V, the velocity. So, this will be Fxi minus Bv, and in fact, we should not write this term. So, the m d2x by dt square, which is the m into a force, is equal to some force which is acting on individual dislocation minus the resistance force because of damping. And now, if you look at this relation, it is very similar to the drag relation. If you are if we have been exposed to this concept, the drag force, the drag velocity relation. So, if a body is allowed to fall freely in the gravity, then there are several forces acting onto it, the gravity force, and then the buoyancy force, and then there is also a drag force, and because of that eventually a body attains terminal velocity. So, drag velocity, it is similar to drag velocity, and hence what you should expect here is that a terminal velocity will be achieved. And what is more is that if the damping force, that is B, if it is large, then terminal velocity is reached much more sooner, Vt is reached much sooner. So, in effect we and we know that damping forces are very large. So, in effect what it means is that we can assume to begin with that the dislocations have attained a terminal velocity. So, to begin with we can assume that terminal velocity has been achieved. So, let me write down this equation over here, m d2x by dt square is equal to Fx I minus B. Now, we have to say B V terminal, and if the body has already, it is not a instantaneous velocity, it is V terminal, therefore, it means that m d2x by dt square is equal to 0, which means that this whole thing is 0. So, this becomes 0, and therefore, this relation further boils down to velocity terminal for the ith dislocation is equal to Fx. When we say I, we are denoting the ith dislocation. So, Fxi by B, or this can be written like 1 by, as if 1 by B is another factor times Fx. So, whatever force is acting onto this into this factor 1 by B, which is now, which can be at many places it is written like m, or the mobility factor. So, this now this mobility is something that we have not touched, it is an unknown quantity, but this is also an experimental quantity. So, this is something either that can be obtained from experiments, or if you are doing simulation you can assume certain values which are appropriate for the given condition. And here Vti, if you are doing a simulation, then this Vti can be broken down to xi t plus delta t minus xi t by delta t is equal to m f x I. So, now we have set up a equation where all you need to know is what is the force that is acting, and you can make certain assumption about this mobility. So, you need to know, you assume, then you optimize this parameter delta t, and this is something that you will begin with some initial guess, and here you will so if you have some initial guess you would get the final value of x I after one step t plus delta t. So, this will be equal to m f x I into delta t plus x I t. So, this relation now allows you to calculate new position of a dislocation given that you know what is the force acting on it, which we should be able to calculate based on what are the stresses being created by other dislocation, and once you have the stresses being created by other dislocation, you just need to use the Peach Kohler relation, which will give you sigma dot b cross E. So, you will know the force acting onto this, and you will have to make some assumption regarding mobility, and you will need to have an initial guess for what is the initial position. Once you have the initial position for t equal to 0, you can keep iterating it to get next and next and next and next position. So, this way how the dislocation is moving, how the shape changes are taking place, all these things you would be able to predict using this relation. So, in this particular one, this is this can be a very simple problem by assuming very simple by making lots of assumption, or you can make it much more accurate and a little bit more complex by adding complexities, like you can add that there has to be a Pearl-Navarro stress for the dislocation to move. You can say that the dislocation they will move only on certain planes, which are slip systems. You can say that there are mixed dislocation as well as edge and screw, or you can say that only edge dislocation is there. So, all this will make it more accurate and more complex. You can add image forces that will act on the dislocation, and there are several other parameters that you can add over here. So, for example, the Berger vector, and so on. So, this is not an exhaustive list. You can keep adding different level of complexity to get a more accurate result, and this system or this dislocation dynamics method is frequently used to understand the behavior of dislocation under different conditions and in different materials. So, we will this introduction to dislocation dynamics, we will leave it here, and when we come back next time we will talk about two systems, one is the FCC and one is the BCC. So, we will introduce, we have only 2 hours left, we will talk about FCC and BCC, and then we will end this course. Thank you.